Hey, I'm Cody. I'm a Bitcoin developer. I work on Fedimint, which is a federated Chaumian eCashment on Bitcoin, and I'm the head of developer support at Fedi. And so this is one of our white paper Wednesdays that we do at Fedimint, where this is going to be our onboarding series for teaching people the cryptographic primitives, distributed systems, Bitcoin, Lightning related things that they need to onboard and start contributing really successfully to Fedimint, right? So Shamir secret sharing is a really important cryptographic primitive. It's actually very approachable and easy. And so like don't be intimidated by this stuff. Like this is like kind of like the best way to like start introducing yourself to thinking cryptographically and doing some fun stuff with cool math, right? This tutorial is a walkthrough of Shamir secret sharing. And we're going to start by defining the problem that we're trying to solve with Shamir secret sharing, solving the problem naively with a couple different approaches. While we do this, we're going to go over a little bit of Fediment of like some of the design choices we made of like why we program in Rust, some of the advantages that we have of that. Like some of the examples in this are in Python, right? But that's just kind of for easy understandability. Fediment itself, the reference implementation is coded in Rust. Solving the problem elegantly with Shamir secret sharing, and then showing how to do distributed key generation, which is something very core to Fediment in order to how do we as guardians where we're trying to be Byzantine fault tolerant such that a couple of us could go malicious. How do we generate a secret in such a way that no one actually knows what the secret is, but we're all able to arrive at the public key associated with that secret, right? Like it's a very cool trick that we do, right? Again, this is white paper Wednesdays. Like we're going to do this as an onboarding series. Every Wednesday, we go over a white paper. You've got like a REPL like this with a good tutorial for it. On Tuesdays is when we do our developer calls. Thursday, we do new contributor onboarding, and we do a deep dive into some aspect of the Fediment code base itself, right? So not like the white paper Wednesday theory code base, just like very deep into the Rust code, getting things running. Like we do a lot of NICs too. But in order to really start jamming as a Fediment contributor, like you really got to be a subject matter expert on Bitcoin, Lightning Network, distributed systems, cryptography, Rust programming, right? And like do a lot of open source development stuff. Is that this is like we do a very good job of like when you come to Fediment, like finding ways that we can like help you grow your skill set so you can be a better contributor, whether that's like contributing directly to Fediment or also doing some of the like tangential projects that we use a lot of, right? So like some of the Lightning implementations, like some of the Bitcoin Core or like other like base layer Bitcoin projects, those kinds of things, right? We've got like a contributor who's going to be doing like a new implementation of a Byzantine fault tolerant asynchronous consensus algorithm, right? Like it's very, very, very fun stuff. It kind of touches every part of the stack that you find it cool, right? There's always a place for you. So please come to hang out with us Fediment guys. So this one's called How to Share a Secret, right? And so the white paper for this is like super short. It's just 2 pages, right? So this is like a good time to also go over some of the kind of like Fediment related stuff, right? But so it's very fun to go through. It's like a very elegant solution to this problem, right? And once you see it, you kind of can't unsee it, right? And it's like just a very, very useful tool, right? So the abstract from the paper, you guys can read that on your own. Like for Shamir secret sharing, it's a way to split an existing secret such that it's reconstructible from any K pieces, but even complete knowledge of K-1 pieces reveals absolutely no information about the secret, right? And so this is a threshold secret scheme. So I'm going to take a secret, I'm going to split it into like 3 of 4 pieces. And if you as an attacker or somebody trying to break the system was able to get access to 2 of those 4 pieces, what's cool about Shamir secret sharing is you actually gain no additional advantages and get no closer to solving the system or solving this, what the secret is, than somebody who didn't have access to either of those. Is that access to any K-1 of, so any of the threshold is T of N, right? Or T or K or whatever, right? So getting access to anything less than the required threshold gives you no information about the underlying secret, right? So it's not like, oh, I got 2 secrets and now I can, with a bunch of compute power, figure out what the last part of it is, right? And we can extend this protocol and use it for with fancier cryptography in order to run a distributed key generation scheme where instead of taking an existing secret, we can actually have a bunch of people adversarially generate a secret that none of them know, but all of them know the public key associated with it, right? Like it's a very cool thing that we use in Fediment in order to make it so that the guardians, none of them is like a trusted guardian. They're all mutually distrustful when they're generating these secrets, right? In the Federation context. So here we go, right? So consider the following problem is that you've got 11 scientists working on a secret project. They wish to lock up the documents in a cabinet so that the cabinet can be opened if and only if 6 or more of the scientists are present. What's the smallest number of locks needed? What is the smallest number of keys to the locks that each scientist must carry? And so you can basically solve this in Python. Like the very naive solution for this one is that you just do a combination, right? Of like, what are all the possible different combinations of these 6 of 11, right? And if you try that out, you just implement the Python code. That's in problem.py. We solve for it using just combinations, and we see that for 6 of 11 scientists, you need 462 different locks for the cabinet, and you need 252 different keys for each scientist, right? But this is just like a not tenable solution to this thing. Like this is completely unreasonable, right? The thing that we want is we want there to be one lock, we want there to be one key, and we want for each scientist to only have to keep track of one thing, right? And so in this case, it's like a share of the combined secret. And we want it to divide it into 11 pieces such that any 6 of them can be combined in order to recreate the key that opens the lock. But if you were able to like compromise 5 of the different scientists, you actually wouldn't be any closer to opening the lock than if you were just some random guy trying to open it, right? And so we just ran this one, whatever you see that initial one, right? So naive solution 1, right? So like, what's like a way that just off the top of our head or whatever, we hadn't thought too deeply about this. We're not cryptographers. What's like a way that I could solve this problem is that I could literally just like split the seed, right? And so if I go over here, I could just take this secret, right? And just like split it in half like an int, and then just give half of it to, sorry, like a string, and give half of it to Alice and half of it to Bob, right? And there I just split the secret. They only have one thing they need to keep track of, all that kind of thing, right? So we can look at the Python code for that, right? And when we execute that, we do Python naive1.py, right? And we don't have to get to that part yet. Is that you know, Dave goes over here, he splits the secret, he gives half to Alice, half to Bob, and then Alice gets half, Bob gets half. They can reconstruct the secret by combining them back together, right? But the problem is this is a lack of security, right? And so where do the security assumptions behind this scheme come from? Is basically the key space over here. Is that Dave has chosen a random number in a very large key space. So like, for example, for your Bitcoin private key is a random number between 1 and slightly less than 2 to the 256, right? And how big is that number? That's the equivalent of like the number of atoms in the known universe, right? And so for someone to randomly guess your key would be the equivalent of them just randomly selecting the correct atom in the known universe. And there's no like way of getting closer. You like figure out what galaxy it is, what planet, what town or whatever, right? So you're just randomly picking, right? It's like the key space is so large, we just assume, like we just act as if it's impossible to guess, right? And so for this one, it's like a pretty small key space or whatever, right? But I'm just doing a tutorial example. And so for this one, the lack of security, right, is that what if the attacker gets a hold of one of these shares, right? We said that we wanted it, if the attacker gets a hold of a share, for them to get no closer to solving the problem than if they didn't have any shares at all or whatever. Well, for this one, if the attacker gets one of these 2 shares, the attacker actually knows what the answer is for half of the key space, right? And so basically he's like cut the key space down into something that's now a tractable problem for him to solve. And so for this code that we're going to go through or whatever, this is like a not very sophisticated attacker. He's using Python for this, and he's going to try a bunch of keys. He's going to do some multi-threading and just like have like 10 threads that are going to be trying these things continuously, right? So let's like go through here, and this is going to be in naive1.py, right? And so this is just like he splits the secret, the attacker compromises Alice and gets the key, and then starts grinding for the solution, right? And so let's go over here and do naive1.py. Cool. And so the key space over here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then it was split. And Alice got the smaller key space. So the key space for Bob that the attacker is looking for is it's like less than 1 million. It's exactly 1 million. Sorry. And so you go over here, right? So the attacker guessed the secret, right? But like, what's happening? Why did this keep going? Well, the attacker, like we said, is not like the greatest attacker in the world. Is that he wrote this thing in Python. And so when he was doing the multi-threading in Python, Python doesn't have a way to communicate across threads. And so you're not able to tell the other threads that you finished the thing that they were doing, right? You basically just allow the threads to finish what they were doing and then just stop, right? Now, this comes into an interesting aspect of Fediment development, is that when it comes, let's do like a brief aside on Fediment development stuff. Well, here's like some other issues with this, is that the solution is not zero knowledge, depends on the ordering of the shares, like all this kind of stuff. We'll come back to this in a sec, right? Let's take a short aside of like, why is Fediment written in Rust, right? Why don't we write the whole thing in Python, right? It's like Python's an extremely useful language, reads like English, you can get an MVP out really easily, yada, yada, right? Like all these things are important. When you're working on Fediment development, this is a distributed consensus system which users trust custody of their funds with, right? The primary concern of Fediment is security. which is why the reference protocol implementation is written in Rust, is that when we write in Rust, we ensure that problems are caught at compile time and they don't sneak past into runtime failures. We ensure that we can correctly implement fundamental cryptographic primitives based off security proofs. So for example, Eric, the lead maintainer of Fediment, he rolled the threshold BLS signature implementation that we use, and that has security proofs behind it. Like it's got audits. It's like, it's very, very well reviewed, right? But it's also like, we're writing fundamental cryptographic primitives here, right? Is like, you don't get to make mistakes. You don't get to bypass things. Like, for example, if you're writing in Python, is that Python has the garbage collector and like all of the crazy memory management through objects and stuff that it's doing or whatever, right? There's like tons of different ways that you can like sneak things past in Python, right? Is like, we do not want those to happen at runtime. We want to catch all those errors at compile time, right? And Rust has a lot of really good, great compile time guarantees that are not available in something like Python, right? So let's like kind of go through and compare like Python, Golang, and Rust, right? Because those are like three very fun languages I like to code in, right? And that you're like, hey, well, why don't you code Fediment in Golang or whatever, right? So Python, we already played with Python and we saw one of these issues, right? Is that the threading doesn't actually exist in Python, right? It's like, this is like simulated threading, is that because of the global interpreter lock, and Python is an interpreted language, and it simulates the threading, right? Which is that only one thread can execute Python bytecode at a time, right? But it simulates threading kind of, but it doesn't have all the advantages of it, right? It's not natively supported in the core language like Rust or Go, right? There's no way to, like in Python, pass state back and forth between threads, right? And so we look at the thread over here, the attacker found the secret, right? But like, it couldn't communicate that to the other threads to kill them off, so they stopped looking, right? And then well, there's ways around it or whatever, right? But like, I quickly implemented that. And so let's try this again in Golang, right? And this is like a really good way to see this, right? Of like, we've got a more sophisticated attacker. The attacker is writing Go for this one, right? And so we look over here, this is naive1.go, right? So this is like the same thing, but the secret string over here is actually significantly longer, right? So let me just copy this over. I'm just gonna illustrate it of like how fast this is. Or when we do this, right, is that this is actually going to take this is going to be extremely fast, right? So Go is a language that has like extremely good concurrent support. It's like concurrency is a first class citizen. It's like super easy to do concurrency stuff within Go, and you have channels where you can so you have instead of threads, you have Go routines, and you can pass the state back and forth between these things through channels, right? So when we finish when one of the threads finds the solution, it can communicate that it's done and then close off the other threads, the other Go routines, right? So let's take a shot at running this, right? So go run naive1.go. And again, this is like the same thing, using the same number of threads for the routines, but Python threads, right? And let's just see how much faster this is, right? So I'm gonna hit it, boom, found the secret, right? Go is significantly faster, right? So let's do like a much larger key space when we're doing the same thing, right? Oh, oops. Cool, right? Is like, look how much faster this is, right? Is that like, so now the attacker is like much more sophisticated. He's able to like search through the space a lot bigger, right? So in terms of like cryptographic security, you're gonna need like a much larger number than this, right? A much larger key space for it to go through, right? But yeah, this will just take a little bit for it to find the key space, find a key. Yeah, right. So attacker gets the secret because he started with which half? He started with, if he finished here, oh, he must have started with this half, right? Which is yeah, he started with Alice's share, right? So that makes sense. Cool. Yeah. So but so like now, so here's like some of the advantages of Go. Why not Go? Why write this in Rust, right? Well, there's a couple guarantees that you get in Rust that you don't get in Go. Is that Rust, you get compile time guarantees of memory safety and thread safety. And so for this one, this is kind of just like a simple program or whatever. It's not too complicated or whatever. What I did over here is this runtime fail is I basically introduced like a kind of subtle bug inside of here, is that this is something that's going to pass the Go compiler, but it's going to cause an issue at runtime, but it's not going to show up as an error at runtime. And the reason why is because the error is not going to trickle back up out of the thread. The thread's just going to panic and die off, but there's going to be no indication that that's going on, right? And so if we go over here, basically what I'm doing is I'm dereferencing a null pointer, right? Which is just like a problem. In Rust, there's no concept of a null, right? It's like your code does not compile if you have memory errors inside of it, right? And so like it's not even possible to get this past the compiler. So if I go over here and do the same thing, I do go run runtime fail.go, right? So it's looking for this thing, and it just kind of looks like it's going slow, right? Is that The reason why it's doing this is because like the threads are airing out, right? But it's not trickling this back up, right? And so this is something where it's like a security concern, right? That's not going to show up until runtime, and it's not something you probably won't catch. And so this is why in Rust won't even compile if you have an error like this, right? And so that's like the issue. So we go over here, we go to my Rust implementation, which is the exact same thing, right? This is just implemented in Rust. And so we go over here, let's try the Rust one, is that I go clear and then do cargo run. There we go, right? And so you can see it's not as fast as Go, right? And I also kind of cheated a little bit because I compiled this beforehand, right? It's like the compiler is slower than it is with Go, right? Especially on Replit, right? Yeah, you can see like, it's doing the multi-threading, right? Like we're kicking off these threads, right? Is that that's up here, right? So we're like spawning threads for when we do that, right? Is that it's searching the key space. It's got very good performance. It's very close to the metal, right? Like, but you get all these guarantees of that. Like if I tried to do something like I did with the Go code, is that it wouldn't even allow me to compile the code, right? And so these are like the security guarantees. Again, Fedimint, we're handling other people's money through these systems, right? Is that we do not get to mess with the security aspect of it. Is that like the performance and the speed, those come second, okay? Cool. So we'll just let this finish as it keeps going, right? So then I go back here. Let's go back to solving this problem, right? So like we're solving this problem again, right? Of that we've got 11 scientists working on the secret project. We want to make a 6 of 11 threshold signature with these guys. Is that we tried 2 naive solutions. We've done the simple combination and then literally splitting the secret. The combination was too complex. Splitting the secret wasn't zero knowledge. What could we do? Well, we could do something like a one-time pad, right? And a one-time pad is just you take the initial secret, you pad it with some random number, you give the random number and secret plus random number out to Alice and Bob, and then they can recover the secret by doing Bob share minus Alice share, right? And so now, because they're just random numbers on their own, like this is a zero knowledge system, right? Of that Alice and Bob achieve no information about the final secret just by holding the shares. There's no different than if they were just like a random person trying to do this, right? And so if we go down here though, we can do the same thing with bytes, right? Of like, this is just implementation with integers, right? This is an implementation with bytes. But we're still missing a couple of properties. Is that Dave still has full knowledge of the secret, right? Of that Dave is generating the secret and then splitting it. And so we're trusting Dave, right? The order in which the secrets are shared is significant, right? So this is not like any 6 scientists could come together. Like you need a specific ordering of them so they know what order to like add or subtract in or whatever it is, right? There's no fault tolerance. It's still not a TFN threshold scheme or whatever, right? Like this is not the best system that we could possibly come up with. And there's probably a more elegant solution. And I can guarantee you that there is. Yeah, this is gonna finish pretty soon, right? There you go. Attacker gets the secret, right? And then it kills the code. Cool. So we go over here, and now we're gonna run the naive 2. Sorry. Naive 2.py. There you go, right? And so here's like the integer level one, like you get a random secret, you pad it with something, you add this together, right? And then the ordering matters when it comes back. And you can do the same thing with bytes, right? Cool. Cool. So let's go to the next one, right? And so now we arrive at like the elegant solution. The elegant solution is Shamir secret sharing via polynomial interpolation, right? And so what's polynomial interpolation? It's that a polynomial is just any y equals, and then the y is equal to some expression consisting of variables and coefficients. And it looks like y equals 3x squared plus 2x plus 1. And we define the polynomial based off of what the highest variable power of the variable x, right? And so this would be a 2nd degree polynomial because this is x squared, right? And if we go down here, this, for example, is like 3x squared plus 2x plus 1. That's a degree 2 polynomial because it's x squared. This one would be a degree 3 polynomial because it's x to the 3rd minus 2x plus 1, right? And then interpolation. So what is polynomial interpolation? Is that normally what people do is they'll like define the polynomial and then plot the polynomial and then pick points along the polynomial on the graph. Is that polynomial interpolation is I start with the points and then I use the points to define the polynomial. And so from the points, I can back into what the equation is, right? And so like Lagrange polynomial interpolation, for example, is like a way that we can do that. It's just some like pretty simple math for just saying like, hey, I give you a couple points and then you plot a polynomial that goes through all those points, right? Cool. So let's do this as an example, is that I do Python polynomial.py. Right, and so I'm just going to write a couple points, and then it's going to draw a line that intersects at all those points, right? So I can do like 1, 1, 5, 8, 8, 20. Okay, right, and so there's 3 points here, and so with 3 points, I can define a degree 2 polynomial. And that's what we're going to see, right? And so I can go look at the thing that I just plotted, right? And we can see those are the 3 points. I did polynomial interpolation to define the only degree 2 polynomial that could possibly have gone through all 3 of those points. There's no other way to draw a degree 2 polynomial that goes through all 3 of these points, right? There's this unique one. Okay, so that's like the thing you have to know about polynomial interpolation. Okay, so what is Shamir secret sharing, right? Is that we can define any polynomial p of degree n minus 1 given n points. And so this is what cryptograph Shamir secret sharing is based off of, is that it takes n points to uniquely define a polynomial's degree n minus 1. And the secret is hidden as the constant term, the y-intercept of this polynomial, right? And so in this one that I just built over here is that with these 3 points, I can define one and only one polynomial of degree 2, so an x squared polynomial, that will go through all 3 of those points. And when I define that, it will intercept the y-axis at exactly 1 point. This is the secret, okay? So this is how Shamir secret sharing works, is that you define some polynomial, you pick a bunch of points along the polynomial, and you give the points out to people. And then with degree of the polynomial plus 1 points, you can redefine the polynomial, you can reconstruct it, and then figure out where it intersects on the y-axis, right? And so let's run the program again, and let's do something. I want to do a 4 of 5 threshold signature or something. Sorry, a 4 of 6 threshold signature. So I would put like 6 random points, like 4 random points in. Okay, that was not a very good plot. Let me delete this one and do it again. Okay. So let's have it be, I want like a 3rd degree polynomial for it, right? And so we'll do like -5, -10. Kill shell. Go back over here. Okay. Python. Okay, so let's do -5, -10, -3, 5, I guess. 5, -20, then 10, 50, whatever. So that should be a 3rd degree polynomial. That kind of looks like a squiggly, right? Well, that's not very good. So it shouldn't intersect it here. This is I chose bad points or whatever, but you guys get the principle. And so basically, I define the polynomial, and then I pick a bunch of different points along this polynomial, and I give out the points. And then any 4 of those points would be able to come back together and reconstruct the polynomial and figure out where it intersects on the y-axis, on the y-intercept, right? And the y-intercept point of this polynomial is the secret. So here we go. Shamir secret sharing, right? So you need the Lagrange interpolation. Here's an example of doing like a 3 of 5. Here's how we'd solve the 6 of 11 scientist problem or whatever. Let's like actually run this, right, to see an example. So let's do clear. Then we're going to do Python Shamir.py. And so the Shamir one that I have in here is that this defines a way to, this is like how we define polynomials. This is evaluating the polynomials at a specific point. This is the Lagrange interpolation one of like given points, redefine the polynomial. This is the secret sharing scheme. And so this is going to be that you enter a secret number and you enter the threshold number that you want to split it into, and you enter the total number of shares that you want to split out. It creates a polynomial, it creates the shares, and then it prints the polynomial and the shares, right? And then after that, we create the secret, we can do a recovery of the secret, right? So let's try this out, right? So here I'm going to create shares, right? Split a secret number into n shares such that any t of them can be used to reconstruct the secret. I'm going to pick a secret number of 560. And the threshold I'm going to want is, let's do 4. And the total number of shares I want to create is 12, right? And so we can take this, right, if we wanted to, and we could plot this on a curve somewhere, right? I could actually do this. Well, these are pretty big numbers. I don't know if it's going to fit on, we can try. So let's plot these using my polynomial thing that I have. Polynomial.py, right? And so I should be able to take any 4 of these and create a degree 3 polynomial, and wherever, and the y-intercept should intersect at 560, right? And so let's just take a couple of these. And 1, so let's try 9, 3, 12, and 5. This might work. Really hope it does. Oh, it was too big, I think. Oh, no, there it goes, right? So we see here, like I drew the thing. Oh, I just have it split off there, right? Is that we see here that the y-intercept is 560, right? And so I did this by taking the points, like a couple random points on these ones, right? But I could take different points, redefine the polynomial, and I would end up at the same point, y-intercept point, right? So I can, let's actually do that again. We'll delete this. And then let's try it again. Okay. So those are the points I did. I did 9, 3, 12, and 5, right? So let's try different points. So I'll try this one. Oh, okay. Oops, sorry. There, so we're trying 7, 1, 11, and 10. So these are 4 different points. Try it again. Check it out. And it's kind of hard to see, but that's 559.99999, right? And so that's basically 560, right? So I think it actually overwrote those points, right? So you can see all the points that are plotted on there, right? But you guys get the idea, right? Is that when I reconstruct this polynomial using any 4 of these shares, there's one and only one polynomial that can go through there, and wherever that intersects on the y-intercept, the y-intercept is the secret. Okay, so there we go. And so instead of doing it visually, let's do this as a, let's do this for a kind of command line recovery, right? And so I take the threshold number is 4, enter the shares, I'll do like this. 1, no, oops, 2, 3, 4, right? And so I do the recovered polynomial, right? And so from these, I use a Lagrange interpolation in order to recover the polynomial. Once I recover the polynomial, the y-intercept, so when x equals 0, y is equal to 560. 560 is the original secret, right? So there we go. That's Shamir secret sharing, right? Is that you define the polynomial, you pick some points along the polynomial, you give out the points, and then any threshold number of those points can come back together, reconstruct the polynomial, and then figure out what the intercept is on the y-axis. And that's the secret. Okay. So that was fun. So now this is like the last section of this, is that we need to solve the Dave problem, right? So what is the Dave problem? Is that up until now, we've had this magic dealer, Dave, who knows the secret, splits the secret into shares, and distributes the shares. And so we want to get rid of the Dave problem, right? And the reason why is because Dave is a trusted dealer in this situation. Is that he has like God mode of that he knows the secret and the threshold is for everybody else. He actually has the full secret himself, right? So in the Fedimint context, we want the guardians to be robust. We want them to be Byzantine fault tolerant so that so for the number of, this is like a Byzantine fault tolerant thing, we'll do this in another white paper Wednesday, is that the number of malicious guardians, in order to be resilient to that number of malicious peers, you need to have a federation size of 3 times the number of malicious peers plus 1, right? And so if M is 1, if one of them can go rogue, then you need 3M plus 1. So you need a federation size of 4. And of 4, you'd want to have a 3 of 4 multi-sig solution, right? What if you wanted 2? If you wanted 2 guardians to be able to go rogue, then you'd have 3 times 2, so 6 plus 1, 7. So you'd want a 5 of 7 solution, because then up to 2 of them can go rogue, right? So distributed key generation is a way of, during this initial process, you don't want to have a trusted dealer, right? Because if there's a trusted dealer, then just he has to go rogue, right? It doesn't matter what the size of the federation is. So how does distributed key generation work? Is that basically everybody is going to do their own defining a secret in a polynomial, random polynomial that goes through that secret. We're going to split up privately those secret shares, and then we're going to give those secret shares to everybody else. Everyone's going to add together all of their points along everybody else's polynomials. And this is why I made the picture at the beginning of this picture look like this. It's going to look like this, is that Alice, if Alice is the point at, is the X at this point, Bob is the X at this point, and Carol is the X at this point or whatever, they're going to add their secret shares together. And because they're adding their secret shares from all of these combined polynomials, you're going to get a sum polynomial, and they're all going to arrive at this points along a new polynomial, but none of them knows what this actual polynomial is, right? It's very important to understand this, is that because we're adding in these way, right? The only thing that I know about, if I'm Alice in blue and this is Bob in red or whatever, the only thing I know about the Bob polynomial is the point that Bob gave me, right? And so I'll add my points with Bob's points, with Carol's points or whatever, right? And we'll add at this, come at this new polynomial point, right? And then everybody else does that. And now you use polynomial interpolation along those new added points to make the new polynomial, the combined polynomial that intersects at the y-intercept, but nobody knows what that polynomial is when they do this process of adding these keys together, right? And so you arrive at a polynomial that nobody knows. And so the secret is you do this distributed key generation where nobody ends up knowing what the secret is, right? It's very, very cool. And so this is the process that we use in Fedimint in order to generate the keys. So we go back over here, solving the Dave problem, right? And so we can add polynomials, right? And it works like this, right? And we add the polynomials, and just like, here's some brief math on it. Like you can, just the same way that you can add polynomials, you can evaluate polynomials at specific points, add those points together, and then when you evaluate the polynomial from those new points that you added together, it will be as if you added those polynomials themselves, right? Which is pretty cool. So DKG and polynomial addition, right? Is that in DKG, a distributed key generation, each participant generates a random polynomial of t minus 1 and creates shares for the other participants. The secret key is the constant term of the sum polynomial, which is just the sum of the constant terms of each participant's polynomial. So when you do this, you exclude your own point, right? This is just like a security thing, right? In the scheme, each participant I generates a polynomial of degree t minus I, where t is the threshold of the scheme. Secret of the participant is the free coefficient of this polynomial. And so they each have their own secret and their own polynomial. They take the points, they distribute them to everybody else. They add the points together. You get a new polynomial, right? That you can only reconstruct if people come together. But during this process, until you reconstruct the combined polynomial, nobody knows what it is, right? It's pretty cool. So each participant has to use the same x coordinate for the participant across polynomials, right? So if I'm at x equals 150,000 or whatever, I have to be at x equals 150,000 for all of the points that I'm given for all these things when I do the polynomial addition, right? That's just another point. So let's like run this and see what it looks like. So I made some code for this one is that if you go to dkg.py, right, this does a distributed key generation. And like you can go through the code for this one. I'm just going to run through it on the right hand side because I'm kind of running out of time. So Python dkg.py. And the way that I do this is I set, I do execute a dkg. I'm going to do 1, right? The threshold is going to be, that would be 5 of 12, whatever, right? So here we go. 5 of 12. Okay. So here we have these participants. We have Alice all the way through Liam. They each generate a polynomial where each of them has like their own secret, right? And so this is Alice's secret, and she has this polynomial. This one is like, Heidi's secret. She has this polynomial, right? They evaluate their polynomials at these 12 points, right? And then they distribute the shares to each other when they do this, okay? And let's just finish it right now, right? Oh, one sec. Okay, back. Sorry, didn't initialize a variable. So to a default value. So if I go over here, yeah, so let's run this DKG, right? So I'm going to do Python dkg.py, and I'm going to execute a DKG. Is that the threshold is going to be, we're going to do 4 of, let's do 7, right? So the participants in this DKG are Alice, Bob, Carol, Dave, Eve, Frank, and Grace. They each generate a polynomial themselves, and then they generate these shares, and then they distribute the shares among each other, right? And so after this, we're going to show how with DKG, you can actually dynamically update the group of who's in and who's out from a federation, right? And so, but for right now, we're just going to finish it up, right? So they finish it up, they distribute the shares, they run polynomial interpolation, and they, so they arrive at this secret over here, 3298, right? But if we notice over here, the secrets that these guys had is not 3298, right? None of these guys knew the secret during the process of this thing. Is that when you do distributed key generation, you arrive at a secret that none of them knew until they actually reconstruct the polynomial, right? And like when they're using these points that they make as the things for signatures, they never actually reconstruct the polynomial in order to figure out what the secret is, right? They basically just use signatures and then combine the signatures in order to make it look like it's associated from the public key associated with the secret, but they never actually know what the secret is, right? Like we don't have to get into that right now. Like that's more of like a later thing. But so let's go over here. So kind of the last thing that we're going to cover for this is that using something really cool and interesting, you can actually do something where you add and remove participants from the DKG, right? And the way that we're going to do this is we're basically going to, the people that we're going to keep involved in the federation. So let's say like Guardian gets compromised or whatever, and the rest of the federation wants to vote him out of the federation, or the rest of the federation wants to vote somebody else into the federation, right? Is that what they're going to do is they're going to offset the polynomial by some random number. And all of them are going to offset their own points of the polynomial by some random number. And so if we're doing it, if we all have arrived at this polynomial, right? And then 3 of us add to the 0 term a certain amount, and one guy is not tracking that addition, well, then he is no longer operating on the same polynomial that the rest of us are. The rest of us are still operating on the same polynomial. And so now by doing this, you can basically remove people from the federation. So let's actually see what that looks like, right? So if I go over here, and then I'm just going to close out and then clear this, and then I'm going to do Python dkg.py. We're going to execute a DKG. It's going to be a 3 of 4. And let's go over here. And what we're going to do is we're going to remove a participant. We're going to remove Carol from this one, right? So we're going to remove Carol. And so after we remove, so if we look over here, oh, it didn't print out the some polynomial between those two. Second. 1 second. I'm going to have to do this just to illustrate it better. So let's do Python dkg.py and execute a DKG. We're going to do a 3 of 7. Okay. So we go over here, got Alice, Bob, Carol, Dave, Eve, Frank, and Grace. These are all their polynomials, right? And let's remove Eve. And after we remove Eve, the new polynomial looks like this, right? And we remember this is a 3, threshold of 3. And so polynomial is of degree 2, right? And then let's remove somebody else. So we've removed Eve, right? And then let's remove Frank. Cool. So we've removed Eve and we've removed Frank, right? And so what do we notice here is that the intermediate DKG secret, right, is updating, right? The y-intercept is changing on this one. The secret is changing. But the secret is changing because what's happening is when we remove is that I'm giving an offset to all of the other people who are remaining participating in this. Is that in this one, right, we subtracted 3, like, what is that, like 200 or no, it's like 176, right? Is that we subtracted 176 or we added negative 176, right? And Alice, Bob, Carol, Dave, and Grace all did that with their points, but they didn't tell Eve, sorry, they didn't tell Frank about that. And so now Frank is operating off this previous polynomial over here, right? This is what he's doing his math off of, but everyone else is doing their math off of this one, right? And so now you can actually, it's like much more complicated to do this one. You can actually bring other people into the federation when you do this stuff, right? Of like, how do we do that? We basically reconstruct the polynomial and we kind of go through this whole distributed key generation round again, and we kind of like recreate the federation, right? But so this is like a cool way that you can use Shamir secret sharing in order to do stuff like dynamically add and remove people from the federation, in order to do this distributed key gen so that nobody actually knows the secret that's underlying the cryptography behind these things. If like, it's like none of them know what it is. It's a very cool thing, right? So hopefully this has been helpful. This was, again, like White Paper Wednesday. We do this every couple of weeks, basically, like whenever I have the time to put like a really high quality thing together like this, right? We'd love to see you in the Fedimint GitHub and in the Discord, right? Like we do a very, very good job of onboarding new contributors. And even if like you're not like a good fit for Fedimint or whatever, like happy to help you as you move off into like other parts of the Bitcoin ecosystem, like get you started working on a Lightning implementation, get you connected to like some other developers to can mentor you and all that kind of thing, right? So really hope you guys enjoyed this. I enjoyed teaching it and I enjoyed making this. So thanks.